to give this talk. I'm sorry I didn't give it a while back. I'm sorry I haven't attended too many of these seminars recently. Things have been pretty busy, but I thought today I would be a little bit indulgent for myself. As most of you know, I finished my PhD in St Andrews late last year. It's actually not almost a year ago that I did my Viva, so last December. And I kind of hadn't had a chance to present the kind of full PhD in its entirety, so I'm going to be extremely ambitious right here and try and present the full thesis or the highlights from my PhD in kind of one talk. And we'll skim past a lot of the details, but I just want to kind of show broadly what we kind of spent the 3.5 years during my PhD doing, and hopefully trigger some discussion and potentially some interest amongst various people here. Now, the St Andrews people know various parts of this already. And just a background to me, I'm now at the University of Aberdeen, doing an independent research fellowship on something slightly different. I'll come on to that kind of at the end. But there's still kind of plenty of overlap between the UCL radar group and some of the stuff that I'm doing. And to kick it off, I have to say thank you to all of my supervisors, because this is obviously a collaborative effort. This picture was on a very, very hot day in St Andrews just before my graduation. And it's a great picture of me, Dav and Duncan, standing by the love of my life, which is AVTIS, or, well, was the love of my life for 3.5 years. And of course, other people, Bryce, who is here or may be coming to this talk, Matteo, Doug, and all of the millimeter wave group. I miss you all greatly, and hopefully I'll come down again relatively soon. So I will very briefly talk about the motivation around AVTIS and Cryosphere mapping and why we want to do it. I don't want to dwell too much on this. I want to get into the results and discuss that a bit more, but just to kind of give some overview about why we would want to look at the cryosphere. So the cryosphere composes all of the ice and snow on our planet. We all know that it's rapidly changing because of climate change, and we can look at very large scale changes, but there are many processes that happen on a local scale, which are also very important, but very hard to measure and observe through satellites in space. So processes such as iceberg carving at tidewater glaciers, where icebergs fall into the ocean, surface melting on alpine glaciers, volcano ice interactions, where you get these big cauldrons forming on the ice surface, lake outburst floods that cause destruction downstream. These are all processes that happen pretty quickly, often at a local scale, but have a large impact on the environment and the people around it. So it's these processes where we need close range sensors to be able to detect and measure the processes driving these changes, and to monitor them for hazard warning systems. And that's where, as I said, close range sensors come in. And this is a diagram which kind of tries to summarize the different close range sensors that people have been using to monitor glaciers specifically, but it also applies to snow mapping. And I put this on here as a bit of a continuum. People on this call will be well aware of the fact that as you increase your wavelength and reduce your frequency, your angular resolution, or just your resolution in general, gets coarser. So there are many people that have used radars such as the Gamma Portable Radar Interferometer, ground-based SAR radars to measure deformation changes at small glaciers, often alpine glaciers, but also at larger tidewater glaciers. These are, let me put my my pointer on here. These kind of encompass these lower frequency radars here. Whilst they have a lower sensitivity to atmospheric obscurance, their resolution is coarser. So many people like to use optical sensors like LiDAR and cameras to get the high detail that we often need to map very detailed processes, especially at, for example, tidewater glacier carving fronts. But of course, when you have poor weather, you can't use these techniques because they can't see through cloud and obscuring conditions. And that is why millimeter wave radar comes into play here. And I know I'm speaking to many experts in millimeter wave radar, so they won't need to hear this, but useful to know that we have this trade-off between sensitivity to atmospheric obscurance and angular resolution when you use millimeter wave radar. But the key thing for my PhD was that no one had ever used it to map glaciers before. So my whole PhD was to try and develop millimeter wave radar, and specifically AVTIS, which I'll talk about in a second, to see how well it can be used to map glaciers and can it be used for monitoring efforts and observations. We also looked at some snow, but that was something that came about largely because of COVID, but I will talk about that a little bit in this presentation as well. So I'm going to be, as I said, very ambitious, talk about various parts of my PhD, just try and give the highlights. I'll skim through a lot of it, but what I want to try and cover in this talk is a little bit about AVTIS, some of the 3D mapping techniques that we were developing, and some data on the radar backscatter characteristics from glaciers, and then look a little bit later at some of the applications that we used AVTIS for in this PhD, and then kind of try and summarize all of that towards the end. Okay, let's get into AVTIS then. So I'm not going to go into the kind of detailed hardware characteristics here, largely because Dav and Duncan are on the call, and I will probably get a lot of it wrong. And I also have a feeling that it's been upgraded recently, so a lot of it might be out of date. So instead, I'm just going to talk about kind of the high level stats and characteristics that were important in this PhD. So AVTIS is a FMCW rule aperture 94 GHz radar. We've got an image of it here on the left. We have the radar head here that I'm circling. It has a Cassegrain antenna, geolocated with a GPS, and it spins around on a gimbal. This is all placed on a tripod that we deploy in the field, powered by two 12-volt car batteries, and all the power supply unit and control box. Everything is controlled through this yellow box. That's where the computer is and the hard drives, etc. Some of the characteristics that are important to note: it has a two-way radar beam width of 0.35 degrees, which gives a azimuth resolution of 6.1 meters per kilometer. In the kind of default setup, or the setup that we mostly used, the range resolution was 75 centimeters with a maximum range of 6 kilometers. Obviously, we can change that if we needed to, and we did, to improve the range resolution. It takes around 50 minutes to scan a 20 by 5 degree area at 0.1 degree increments, just to kind of give an idea about how long it takes to scan. It doesn't take too long, but you have to be wary of the fact that the scene can change during data acquisition. And always useful to know that it's relatively heavy. The radar head is around 40 kilograms, and because you've got to have two car batteries, each weighing 23 kilograms each, there's a lot of carrying of stuff. So you can't walk too far with it, as we found out on many field trials during my PhD. And this video I've been using in pretty much every AVTIS presentation I've been given in my PhD. And it's really nice because it shows exactly what it does. It scans from left to right, measuring radar backscatter along each line of sight. And as it scans from left to right, it scans progressively higher in elevation so that we get the full scene of the area that we want to cover. And by doing that, we can acquire nice 3D data cubes of radar backscatter at each range bin, azimuth angle, and elevation angle, which is kind of what I'm showing here on the left. It's actually in Cartesian coordinates, just to make it more complicated for you. But it just kind of gives an idea that we have all these data sets at different elevation angles, giving us lots of information about the characteristic or the radar backscatter at different areas of the scene that we're looking at, which can tell us potentially a lot about the surface characteristics. And on the right-hand side is a 2D plot. So what we often do with these 3D data sets, we want to do some 3D mapping, but I'll come on to that in a minute. But we can produce these really nice 2D plots where we squash the 3D data cube down, and we produce these what looks like a SAR image. It's not a SAR image, but I guess can be interpreted in a very similar way to that, and it's very pretty. This is of a glacier calving front in Svalbard, where we did some work. I'll talk about that at the end of this presentation, but the images are stunningly beautiful in my opinion, and can offer us a lot of information on the characteristics of the terrain. Okay, so that kind of gives an overview of the motivation of my PhD and the whole project as a whole, and AVTIS. But now what I really want to do is to delve into some of the results of this PhD and try to show you kind of what we were doing for 3.5 years and some of the developments that we made. So the very first thing that we wanted to do was to improve upon the surface extraction methodology that Davin Duncan had developed over many years for extracting 3D point clouds or 3D surfaces from the data cube that AVTIS generates. And we had a very nice data set from a local quarry, Balmoral Quarry, which the St. Andrews guys will know very well. AVTIS was used to map this quarry, which is this quarry up here. But the neat thing about this this data set was collected back in 2014, so before I was around, but there was a high resolution laser scanner validation data set that we could use to validate different techniques for extracting 3D surfaces from the data. So it was the perfect and ideal opportunity to play around with some new techniques and actually be able to extract to quantify the performance. This is an absolutely horrendous slide. I'm really sorry about this, but I thought I would just put this in because with AVTIS, when AVTIS scans across a scene of interest, we spatially overlap. We overlap in space, so there's a lot of overlap between the beam footprints on the terrain. So we kind of had this idea that we could potentially use the redundancy in the information that is acquired by AVTIS to see if we can improve the signals in the radar data to improve the surface elevation extraction method. So what I've drawn here on the left-hand side, and I'm not going to go into the details of this, this is all in a paper which we hope will be published soon, is to just try and formalize a way of defining how much overlap there is between sequential beam footprints at different elevation and azimuth angles. And what we did was just define a few mathematical formulas to do this, which is what I've shown here on the right-hand side. And all this is basically saying is that depending on your increment in elevation and azimuth, you can define how many waveforms, how many line of sights, which I'm calling waveforms here, overlap in space. And they overlap when the distance between the beam footprint center and a subsequent beam footprint center is smaller than half the two-way beam width, which is what this equation is showing here. Basically, we're just following the Nyquist criterion to make sure that we are spatially overlapping, but it's following kind of standard signal processing rules of thumb. May not have described that possibly in the best way. It has been a while since I've looked at this in detail, but effectively, we overlap in space. We can use that information. How do we use that information? Well, very simply, we can use it to average different waveforms to improve the signal to noise ratio of our range profiles, of our line of sight radar backscatter range profiles. And that's what I'm showing here. So I've just taken a segment of one particular line of sight between 3,000 and around 3,450 meters range. The gray signal here is the original signal that AVTIS measures. The black signal is the averaged signal from all of the line of sights that are within a beam footprint. So you can see straight away that the noise is suppressed. The signal is a lot less noisier. We can start to see different terrain echoes in this signal. We then smooth that, as you can see in the red line, and now you can see that we have 1, 2, 3, 4 different echoes in our signal, which are resulting from the radar signal backscattering from the terrain. And we can easily pick out one of these terrain points and say that is the range to terrain. But we can also use a relatively simple statistical criteria to say anything above two times the standard deviation of that resulting range profile. If there is a terrain signal that is above that threshold, we can also extract all of those terrain points. So we have a method to extract just one single terrain point, but also multiple terrain points to increase the density of points in our resulting 3D point cloud. And if none of that made sense, it doesn't really matter too much. But I guess the easiest way to look at this is that once we do all of that extraction, we develop an XYZ point cloud that represents the surface in XYZ. And if we use the original method, which didn't do any averaging at all, then we have what we see on the left-hand side, which is a relatively noisy point cloud with quite a lot of spatial variability. This is of Balmoral Quarry, so we have the surface kind of, it's essentially like a contour that we can see here. And this is all various other parts of the terrain colored in SNR. But when we apply the waveform averaging, we suppress a lot of that noise, and we're also reducing speckle. So this is also part of the reason why we're doing this, is that by doing this by applying this methodology, we're reducing speckle, which does impact our terrain extraction algorithm, and introduces quite a bit more, not noise, but anomalous points in our point cloud. So you can see we've got a lot of improvements here, and we quantified based on our validation data set what the improvement in performance was. And there's a lot of numbers here, but the key points are that in this top row, we've got this single or multiple point cloud methodology. So when you just pick out one terrain point and multiple terrain points, these are the uncertainties, 2.7 meters, 3.1 meters. But when you apply the waveform averaging method, we have a really big reduction in the point cloud uncertainty. So it's really improving the accuracy of our point clouds, which is really important when you want to do 3D change detection. And the only final thing that we also developed in this particular part of my PhD was also to develop a method of automatically removing any point cloud outliers. I'm not going to go into the details of this because I just don't have time today. But essentially what we did is we used something called a Voronoi diagram, which maps out spatially isolated outliers in our point cloud, pick them out based on some processing, and by the end of all of that processing, we're able to remove all of those spatially isolated points and get a really nice kind of stable point cloud that has been filtered of all of the noise automatically with no intervention by humans, by us. So it's a really nice method, I think. Works well for AVTIS data. We haven't tested it on other data sets, but it's I think a neat method to try to automate the surface elevation extraction method as much as we kind of possibly can at this stage. And as I said, all of this is going to be coming out in hopefully a paper relatively soon. It's a pretty dense paper. We have lots of information in it, but all of that is kind of described in there. Does anyone have any questions on that part? I'll just wait 10 seconds in case anyone does. If not, I will speed on through to the next part. So that first part of the PhD was all about just understanding, you know, how well can AVTIS map 3D topography, what new methods can we implement, and can we quantify the uncertainty of it? The next stage is then trying to think about, well, what information can we gain from looking at the radar backscatter data? And I said at the start that one of the main motivations of this project was the fact that no one had ever used 94 gigahertz radar to look at glaciers before. So one of the things that we didn't have any information on was exactly how what were the characteristics of radar backscatter from glacier ice at this frequency. So one of the first things that we did was try to get out to a glacier, a relatively accessible glacier, to try and get some kind of raw data from a glacier. And we went to Runnergletscher in Switzerland, which Jonathan will know well, as he was also out there a week before we were. And at that stage, we didn't even know each other, so that was a weird coincidence. And we took AVTIS out there because this glacier is relatively accessible. It's got a cafe nearby, so we can drive our car up and carry it a few hundred meters down to the terminus. I won't go into the shipping issues that we had. Duncan can talk about that if he wants to. And I really like this picture because it's a great picture anyway that Dav took, but you can also see two of my supervisors doing all the legwork on the ice while me and Dav just sit and play with the radar all day. And it was a very fun trip. So before I get into the kind of the highlight results, it's always nice to look at a good radar image. And what I've shown on the left is a satellite image, or sorry, an aerial image of Runnergletscher and its terminus region. This here, which we were talking about just before, I think many of you came onto this call, is a tarpaulin cover over an ice cave. It's a horrible feature. It just looks disgusting. But obviously the Swiss like to save their glaciers so they have more economic activity. So that's that part. This is the proglacial lake. This is the glacier. These are this is the bedrock and some bedrock over here and the moraine. On the right-hand side is a SAR image of more or less that exact same place. It's not georeferenced, this right image, so it's not maybe completely aligned, but it broadly is in the same region. And I always like to say this is the first ever 94 gigahertz radar image of a glacier, which is, from our understanding, true and really exciting. And it's neat because you can pick out really nice features in this image, icebergs, which are not in this image, but were when we were there. We can pick out bedrock, where the glacier margin is. You can even pick out some of the crevasses on the surface. And also, interestingly, we can penetrate through this tarpaulin cover and map some of the, I'm not sure what they are, crevasses, maybe part of the ice grotto cave that's under there, some wooden planks, metal features, lots of different clutter elements under that tarpaulin cover that we're also measuring under there. So that's just a kind of overview of some of what a radar image looks like. When we look at a glacier like this, we did some calibration using trihedral reflectors. I'm going to kind of whiz past this bit because it's less interesting, but we just used the radar range equation to calibrate the radar received power and did some geometric corrections of that. But this is the key result, really. When we combine all that data and we kind of plot it out, we find that the data set here, so this is a sigma naught, the normalized radar cross section, which is the value that we were trying to quantify. When we plot that up as a histogram, as I've shown here, it very nicely fits a log normal distribution, which broadly, I would say, is consistent with a rough surface at this frequency. And I think because of the very good fit, I think it's, where is it, R squared 0.99. I think that very nicely shows that at this frequency, a glacier surface is particularly rough. I'll come back to some of those stats on the right-hand side in a second, but many of the features on the glacier surface are kind of consistent with that idea. We have lots of microscale roughness elements and ice crystals around the size of the radar wavelength, so around 3.19 millimeters. We also have streams and undulating surfaces and varying degrees of debris and rock around the margins, which are altering this surface. So it's a very heterogeneous surface. It is a glacier ice surface, but there's debris, there is meltwater, there is various other elements here that change the clutter elements. So I'm very keen to call this the radar backscatter characteristics of an alpine glacier surface rather than a glacier surface, because I suspect it will change if you go to different places in the world. But it's important to kind of realize that all these elements are there in this glacier. So going back to some of these stats, what we've kind of shown then is that it follows broadly that distribution, but when you compare this to some of the literature values, there are some very clear differences between glacier ice and different terrain types. So volcanic terrain is the easiest comparison because that is data that Davin Duncan collected over many years in Montserrat with AVTIS, so it's the most comparable. Very clear differences between the sigma naught normalized radar cross-section values for ice and volcanic terrain. Sand, okay, maybe not as useful a comparison, but if we look down at the bottom, there are clear differences between how glacier ice looks and how dry snow and refrozen snow looks like. So it seems to be the case that glacier ice more at least the ice that we were looking at fits seems to be mostly comparable to wet snow, which is not that surprising because we were there in summer in September when the ice was melting quite a lot, so there was a lot of meltwater. The ice was near the melting point, so it's not that surprising that we're seeing characteristics very similar to another wet cryosphere environment. And yeah, I'm not going to kind of go into that too much, but of course, when we have this data, it means we can actually start to predict the performance of a 94 gigahertz radar when it's mapping glaciers. And this is what I've done here for different instance angles. So just simulating the SNR for a radar at different ranges, or say a radar using the characteristics of AVTIS under different weather conditions. So I think the key thing is that we seem to have pretty good glacier mapping performance in most weather conditions, but rain is probably still going to be problematic at long range. But for long range mapping under other weather conditions, I think a glacier is a pretty good target. And at close range, we're still doing pretty good, even at kind of high instance angles. And this is all out in a paper. This is the exciting part now that I get to say that this stuff is published. So if anyone has any critical parts, doesn't matter. It's published now. Does anyone have any questions on that part? I'll wait 10 seconds again in case anyone does. Okay, I will move on to the final two parts then to look at the two application areas that we were interested in. Well, it's kind of interesting that we were never really that interested in snow at all. This was always meant to be a PhD about glaciers, really. But then COVID happened. We couldn't get to the Arctic, so we were thinking, well, there are no glaciers in the UK, so what else can we look at? Oh, snow will do. Which is also quite interesting and also very important in many different ways. We went to the Cairngorms in March 2021 during the lockdown. That was crazily difficult to get the permissions to drive 3 hours up the road, as you can probably imagine during lockdown. We went up to Cairngorm Mountain Ski Centre, if anyone knows what that is, and we took AVTIS and a laser scanner from Lancaster. So Mike James from Lancaster kindly lent us his laser scanner to act as a validation sensor. And we were coming up to measure the snow cover characteristics of snow across the two corries in the northern corrie region of the Cairngorms. And I like this image because to anyone outside of the radar world, they maybe don't always see the benefit of radar in these conditions, but when you look at the data sets from the laser scanner and the radar, when you have these obscuring conditions, we don't struggle with this at all. We get good data of the scene despite how bad the obscuring conditions were. And this is kind of portrayed here. So I'm showing these 2D scenes again where we collapse that 3D data cube into nice SAR looking data sets. And on the left-hand side, we have the 2D images of Corrie Cass, which is where this ski center is. So you can really clearly see there's a funicular railway in this in the ski center. The actual ski center kind of buildings are down here at the bottom. And we mapped this over 2 days, same with Corrie and Locken, which is the corrie to the right. So that's this corrie here. It was a little bit trickier to map this particular corrie because a lot of it was obscured by the geometry that we were in. But it's very nice. You can very clearly see that on these top two images. This is the first day. I said it's day 2. Day 1 data was not that great. Day 2 data was okay. You can see that generally SNR is a little bit lower than we measured on day 3. And that kind of implied to me there might be some changes in the snow conditions in this region. And that's kind of exactly what we found. So I will show some spatial images in a minute, but to kind of indicate the changes that we were seeing in the radar backscatter data. Now, we just measured the whole Corrie region, so we had a mixture of snow, some ski center elements, we had bare terrain. So there's a bunch of stuff in this data that we couldn't pick out. That's kind of really quite complicated and would have been a lot more work. So we were just interested to see what were the bulk changes in the scene that we could see in the data. So in this first plot, we're showing the sigma naught values as a histogram on day 2. You can see it's broadly just one single distribution. We do have a little peak down here at high sigma naught values. Just going to kind of ignore that a little bit, but most of the radar backscatter values, the sigma naught values, are in this single distribution that we think is broadly characteristics of everything, bare terrain and snow. Then if we then map that, when we map that same area on day 3, we can see that the distribution changes. We have now 2 different peaks that we think are representing 2 different terrain types. So the bare terrain has a mean that is slightly smaller than we had on day 2, but it's broad ballpark in that kind of same magnitude area. The second peak is much larger now. We now have a second peak with a mean of around, okay, it says it there, minus 5 dB. And we think this is being caused by the temperature in the region reducing, going below freezing and refreezing all that snow. Whereas on day 2, we had temperatures above freezing, so we think that the snow was melting and reducing radar backscatter because of the absorption of the radar wave into the snow. That's our interpretation anyway. It seems to kind of make sense to me from the physical perspective. But there were also some interesting elements in the data that we found. So when we started looking into the spatial characteristics, we found one particular region that was very interesting in this region here. So this is Corrie an Lochen. This is an image of the Corrie here on the bottom. This top image shows that exact same region that exact same region mapped by AVTIS, but we're now plotting this in changes in sigma naught from day 2 to day 3. So any positive areas show increases in sigma naught, and we found this region of increased sigma naught across this area of the Corrie here. Seemed quite interesting, seemed to be anomalous to the other regions, to the general pattern that we were observing. So we started looking at some of the images that we took. We didn't have any time-lapse cameras, but we did have some images to kind of see if we could see any changes. And we did notice that there were these rather interesting features in the images that we took. Now, when you look on the first day, now there are some complications because the sun angle kind of illuminates this quite a bit more. But this is the first day, or day 2. Everything seems to be relatively stable. Whereas on day 3, we get this area here with these features. Now, when we spoke to the Scottish Avalanche Service in the field, they seemed to be very adamant that there were some snow surface failures in the region. They couldn't tell us exactly where, but this seemed to tally up with this data that we had here, and it kind of implies that what we're measuring, the increase in radar backscatter, is due to avalanches on the side of the Corrie. Now this was kind of completely unexpected. We were not expected to see anything like this at all, but it's very nice because it is demonstrating to us and to the Avalanche Service that we can map hazards like snow surface failure events, which is very useful to Avalanche Services to know where those events have occurred, because this is only post-event information. And to use that for some kind of hazard warning system. Now, I don't know exactly how that would necessarily be used, but we've just proven the case that we can map it and show where these events are occurring. And we think that generally what's happened is when we look to the meteorological data is that there were quite high winds overnight. We think that the snow from the plateau region of the Cairngorms has been blown to the edges of the Corrie. That's formed wind slab. And that wind slab has then failed, causing these avalanches. So that's the story that we seem to have found. We haven't found any reason for that not to be the case. So yeah, quite interesting, I think. And we did also quantify the kind of similar to the glacier data. We quantified in that specific region around the avalanche what the radar backscatter characteristics were. So if you concentrate on this right-hand plot, we yet again find a log normal distribution when we plot this histogram. Again, characteristic of a rough surface, that makes sense. Snow surface failure, snow rubble, that creates quite a rough surface. So that makes sense to us. Then when you plot this as a function of incidence angle, that also implies that there is surface roughness is the key feature of radar, or the key driver of radar backscatter, because we get high sigma naught values at high incidence angles, where in theory it should be reducing. So all of that put together, this is all providing evidence to us that this is all the radar backscatter increase that we see is all because of a snow avalanche. Okay, I'll leave that for 10 seconds again. We are hoping to publish this paper as well. It's in review at the moment. I think it's with the editor, so I would love to see what the reviewers think of this. Does anyone have any questions on that? I'll wait 10 seconds again. If not, I will then dive into the final case study that we worked on, which was looking at iceberg carving in Svalbard using the AVTIS radar. Now, this was a fantastic field campaign. It was cancelled because of COVID, so there were lots of complications with getting out there in the end. But won't go into those details. We got there, we got some fantastic data, and some of the results seem really exciting in terms of capabilities from a radar perspective. Haven't really had much time to think about the glaciological implications of the data, but what I'll show here is just some results that were in my thesis relating to this field campaign, which probably need a bit more work to get to a publishable state, but at least kind of shows what we think is possible. And this was the area that we were working in. I mean, you can't really get any better than this. This is just amazing, amazing stuff. So I think I presented some of this work to the UCR radar seminars some time ago now. But what we did is we deployed AVTIS again to image this glacier carving front. We also had a time-lapse camera and the same laser scanner that we used for the snow campaign. I'm not going to show any laser scanner data here. That just don't have time for that today. But we are using that for quantifying the uncertainties of the 3D point clouds. So this is what the data looks like. I showed an image of this before. This is again a kind of SAR-looking image of the glacier carving front. And if I play this animation, so if it works, you can see the glacier changing over time, all these icebergs in the fjord moving around, and lots of carving events happening across the carving front. So you can see the ice retreating over time along this carving front. All of this stuff back here are crevasses that we can measure, that we were able to map with the radar. Yeah, so what we wanted to do was try to detect some of these changes to try and measure how much carving was happening at this glacier. And yeah, okay, yeah, just very briefly, the point cloud uncertainties that we measured using the TLS data as validation were broadly consistent with what we measured before. So this is just kind of demonstrating that we weren't getting any ridiculous uncertainties that we weren't expecting. So everything seemed to be within the realms of the uncertainties that we had before, which was promising. Okay, so in terms of detecting carving events, it might seem quite simple. There must be a big change in the carving front, but the whole tidewater glacier carving front is changing all the time. So how you detect carving events is actually a little bit more complicated than just saying there's a carving event. We wanted to develop something automated. So what I'm showing in this top image here is a 3D point cloud between two different dates, two different time periods, 16 hours apart. So one scan, then a second scan, 16 hours later. And it's showing the change in the range from the radar of the carving front between those two scans. So a negative change means that the carving front has retreated. A positive change is the advance of the carving front. And you can see that there is a pattern of red positive range change of the glacier advancing towards the radar. But then when you have these big blue bits, the negative range change, that is where we get the carving event. That's what we want to detect. Now, the way in which we were doing this is that we have a measure of level of detection. So this is just based on the variability of the point cloud around specific regions. So it's kind of it's a measure of detection level at the 95th percentile level. And then if we combine that with the uncertainty that we quantified before, we can set a threshold based on those two values to detect where is there significant change in the point cloud. When we do that, we don't detect all of these carving regions. What we detect instead is a small cluster of points. So when we have that small cluster of points, I've then just implemented a region growing algorithm that just spreads the number of points from that cluster across the whole of the area that encompasses the negative range change. And then that gives us the location of the carving event and the size, the area, and the volume as well, because we have the 3D data to do that. And combining all of that together then, what we've been able to do is generate a time series of terminus change from the very first date, 26th of July 2021, all the way to the 2nd of August, sorry, 2nd of August, yeah, 2nd of August 2021 as well. That's slightly wrong. Oh God, that's in my thesis. Jesus, I can't believe I never saw that. Anyway, what we see is retreat of the carving front over 8 days. That's not surprising. We're now trying to use this to try and understand the dynamics of the glacier. So we've mapped out the changes across the whole terminus, the western terminus and the eastern terminus, and we can see slightly different changes. And we actually kind of we see a difference in ice dynamics between different regions of the glacier carving front, which is quite interesting. We've also been able to map out the velocities of the glacier from the start to the end. I'm a little bit cautious about these, if I'm being honest, because there's a lot of averaging going on here, and we might need to redo these. But what we did see, and I'm not sure if it's real, but I'll just say it anyway. When we get peaks in the velocity, so kind of here, 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 and here, these seem to lag increases in air temperature. So one hypothesis might be that the terminus velocity increases as air temperature increases because of the increase in meltwater. I'm not sure if that's what we're actually seeing, but that's what I wrote in my thesis. So, and no one seemed to pick up on it. Well, no, I think someone did. I think Duncan did and Bryce did. And I just decided to leave it in. But yeah, so that's the data that we have. I'm not really going to go into the glaciological implications too much because we just haven't got there yet. But you can see that this information is going to be really useful to understand ice dynamics. And we can also look at carving processes. So on the left-hand side, we have a time series of a specific area of the glacier carving front where we saw this massive carving event. And if we look on the right-hand side, we're showing a time series of 3D changes in that region. So what we see is in this blue area, that's the start of the time series, we can see an ice foot. So this is sea level. This is the top of the ice cliff. We can see an ice foot near sea level protruding from the ice front. That then advances, retreats back to around here. We then have an overhang, which is being caused by melting at the waterline. And that melting causes instability, and it causes this massive carving event at the end of the time series. And we can see that in the radar data when we look at the 2D scenes, before and after. This is what it looks like before, that's what it looks like after. In the radar data, you can see this nice little peninsula that is protruding from the ice front. That's the overhang. When it all collapses back, you can see that we get this really nice rough radar backscatter scene there, which very nicely corresponds to this area here. And it's, I guess what I'm really showing here is demonstrations of things that we could do, things that we could look at in the radar data to potentially look at carving processes, which is useful for glaciologists. Yeah, I'm not going to skip that one. We also, we quantified a carving rate, which is basically how much the glaciers were retreating by over the period of time that we looked at, combined it with other data to basically show that the glacier is losing a bit more mass than we think it is, but actually this is probably all wrong. It's more just demonstrating what we could potentially do. That is basically everything. As I kind of said, it was ambitious to try and get through all of that in one talk, but I've almost done it. I've got just 2 slides left. What next? We published a very small review paper earlier this year, late last year, kind of just going through what we think needs to be done next to keep improving this method and this technique. So we think we need to try to bring AVTIS to new glaciers with different dynamics, different sizes to see how well it performs in different regions. We were looking at quite small areas. How does it perform at some of the big glaciers in Antarctica or Greenland? Can we use this radar for observing those systems? We need more radar backscatter data. We have done one study. We need way more from different glaciers, again, from different environments to see if it changes in different areas that we look at. We still need to improve the surface elevation extraction processing. I think what we've done is quite good, but it still needs more work on it to make it better and to improve performance, especially the speed. And it's a heavy radar. Can we improve the practical deployment of the radar in the field? Can we do some better radar calibration techniques? A lot more that we can think about there as well, I think. That is everything. Very quickly now, I'm here in Aberdeen. I'm now working on slightly different stuff. I'm working on digital twin technology applied to the cryosphere, so digital twin of glaciers. Still working on remote sensing, and I put in there ICEYE because there may be some links maybe with this group in terms of using commercial satellite imagery for looking at glaciers. Getting into machine learning because that's just what everyone seems to be doing nowadays. Still love glaciology. Was in Svalbard again this year and just loved it. Can't get enough of it. Yeah, and that's what I'm kind of up to. You can contact me on Twitter, website, or email. Yeah, happy to take any questions, comments, anything at all that anyone has. And thank you very much for listening. I hope it wasn't too much. Probably was too much.